Uh, hello, hello, good
Hello,
evening.
sir.
Am I audible?
Good evening. Yes, sir.
Okay, okay, thank you. So this is week 4 online live session for the NPTEL course on urban utilities planning, water supply, sanitation and drainage. This course is taught by Dr. Devapratim Pandit. He is a professor in Department of Architecture and Regional Planning at IIT Kharagpur. And I am the teaching assistant for this course. I am Vaibhav Kabadwal. I am a research scholar in the Department of Civil Engineering, and my area of research is environmental engineering. I am from IIT Madras. So, in this lecture, we will discuss about pumps and service reservoir, and we will solve some numericals, MCQ, fill in the blanks, and match the following. So, till now we have discussed about population forecasting, source and types of intakes. So, why we will just I will try to just give you the idea like how much we have done and what we are going to do, because that will give you the idea of this subject. So uh, so we are here for urban utilities planning for drainage, sanitation. This is the subject name for water supply, sanitation and drainage. So water supply we can get from water treatment plant. So and water treatment plant are made for at least 20 to 30 years. If we are going to make water treatment plant from now onwards, 2 years will, let's take 2024 is the present year. 2 years it will take to construct the water treatment plant, and let's say we are making water treatment plant for next 30 years. So we need to design it for 26 2056, because it should cater, this water treatment plant should cater the requirement till 2056. So what we will do, so for that we need population forecasting. And with that forecasted population, we will multiply it with liter per capita per day, means water requirement by per person per day. So then we will get the water demand for future. So this is the concept which we use to get the design uh, uh, water requirement. And after that, for this 2056, we need to have a water source. So water source can be groundwater source, water can be subsurface source, that means groundwater. And in surface source, it can be rivers, it can be lake, it can be springs. So these are the water source. And for subsurface, we can go for well, different types of wells we studied in in the previous session. So then we did population forecasting. We understood source and its type and type of sources. Then we understood about intakes. Intakes are the structures which are used to uh, take the water from the source itself, and they will transfer the water to the either to the household, and either they will, or they can supply the water for treatment plant for treatment. And in this lecture we are going to study about pumps and service reservoirs. So the pumps are the integral part of the this supply system, whether it is wastewater supply or water supply. And in future we are going to study about water quality parameters. We need to know what are the water quality parameters, which will help us to know how much is the concentration of pollutant And after knowing the water quality parameters, you will understand what is the treatment, what treatment we can give. So this is the whole flow of the subject. And there is one more thing. One. So here is the community. People are staying in one community, and this is the river. This is the river. So what happens? They will take the water. They will utilize it. One community will use the water, and they will produce wastewater. So this they are using it. For using it, they will not directly use it. They will intake structure they will make water treatment plant, and then they will take the water. Same way, they will produce the wastewater. They will make wastewater treatment plant, and then they will discharge it. So this is the criteria which we are following. So what is happening further at a very after some distance, let's say this is city 1. So now we will go to city 2. So city 2 is at downstream. So this is downstream. Upstream means water is flowing this way. So after wastewater treatment plant, the the pollution load is not zero, though it has been reduced, but it is not zero. So some pollution will travel, and some that pollution will be diluted by the river. And here is city 2. So the city 2 will take the water from here. So this is the intake. This is intake 2. This is intake 1. City 2 will take the water, and again they will produce wastewater, and again it will discharge wastewater treatment plant. So this is the flow of water. So if you can see here, from intake to water treatment plant to city, and then city to wastewater treatment plant to again river, we require pumps. The water will not flow automatically. So for that we need pumps. So that's why pumps are the integral part of utilities planning. Hi, can you hear me and can you see my presentation?
Yes, sir.
Okay, thank you. Are you getting whatever I am teaching?
Yes, sir.
Okay, fine. So now, so this is the first question. For increasing the discharge, pumps are connected in series or parallel? Can you text what is the answer? So let's say I depict pump like this. So if you want to increase the discharge, If I keep two pumps in parallel, let's take the scenario. So the discharge will be, let's say Q1, let's take 10 meter cube per second per hour, let's say. And it has also same discharge, let's say 15 meter cube per hour. So if I'm keeping them in parallel and these two pipes, let's say, the diagram will give you the idea. This is just single pipe, so like this you can see. So these are in parallel. This is pump 1, pump 1, pump 2. So if this is Q1, this is Q2, here I will get Q1 plus Q2. So for increasing the discharge, the pumps are connected in series or parallel. They need to be connected in parallel. For providing more energy head, pumps are connected in. So for this purpose, the pumps are connected in series. Likewise, if I make like this is pump 1. It can supply water till this height. Let's say this is H1. If I keep it in series, if I provide here pump 2, it can further supply water at this height, H2. So total head which can be provided will be H1 plus H2. So if you need more energy, more head, then pumps should be connected in series. Which of the following is not a reason for lifting water using pumps? So they're asking not a reason. To lift water from a river or well. Yeah, like I discussed, to lift the water from river or a well, we use pumps. To lift water in a treatment plant, we need pumps. To lift water into the distribution system, we need pump. To boost pressure within the distribution system, yes, we need pump. So the answer is none. Which of the following statements are incorrect about pumping stations? Pumping stations can be located near water treatment facility. Yes. Pumping stations can be located near water storage facility. Yes, they can be. Main pumping stations supplies water to the distribution system. Yeah, main pumping station, they will supply water to the distribution system. And booster we will study further MCQs. Pumping stations are not required in the sewerage network. This is incorrect here because in general what we study, like sewage flows under gravity. You might have studied. That is correct. Because we provide it as open channel flow. Because we say sewage flow is open channel flow. Open channel flow means while flowing, only atmosphere pressure is acting and and it is flowing due to gravity. Due to gravity. This is called open channel flow. So, but what is happening in sewage flow? These are the sewers. So the sewers are laid at a slope. So due to slope, we need more digging of the soil. More dig, more digging. Let's write it as more excavation. So suppose if it is your, this is the home. From the home, let's say this sewage is flowing. So if treatment plant we want to make, then we need to excavate more and more. So what we will do, we will do in like this. If we go for slow, we have to go like this. But we will not go this way. We'll go for smaller things, and then we'll pump. Then we will again provide sewers that will flow under gravity. Then we will again pump. Then we will again. So likewise, here we have to excavate this much. But here we have to excavate less. But the pumping cost has increased, but it's fine because it is more economical than excavating this. And the treatment plant we have to make underground. That is not a feasible option, as we can make, but we have to check the feasibility. We need to check so many factors like uh, soil strata, uh, topography, water, groundwater table. So many things we need to check. So we can't go much beyond because we may have the water table here also. So because water table is there, so it can interference with, so it may have joints. Sewers are the pipes, so they may have the joints. So joints are most of the time leaky. So it can interfere with the groundwater. So that's why we are not going much deep. That's why we are pumping so that uh, we can again provide the gravity flow. So that's why pumping stations are required in sewerage networks also. Which of the following statements which of the following statements are incorrect about pumping stations? This is the high lift pump. High lift pump pumps directly into the distribution system. Pumps which directly send water to the distribution system increases the pressure located anywhere in the pipeline. High lift pump is used for lifting sewerage to a shallow sewer, is used to convey storm water to STP or outfall. So what is the answer? High lift pump are used for directly sending the water into the distribution system. The answer is A. So they will directly discharge the water into the distribution system. So that's why the name is high lift. High lift means from service reservoir, they will directly lift the water to the whole distribution system. So this distribution system is the city. So in city, This is the service reservoir. This is the service reservoir. From this service reservoir, the water will be discharged to the. This is plan view here. Suppose this is the city. So you can see in the roads, these are the pipelines below road. Pipelines below the road. So for that, high lift pumps are required. Among the following the correct statements regarding water supply pumping operations are: rotary pumps are suitable for handling liquid containing suspended matter due to the close fitting on the rotor. Because of the close fitting on the rotor, they can't handle suspended matter, because that can affect, because they are closely fitted, so that will affect the mechanical parts. Mechanical parts may undergo more maintenance, so that's why it is not suitable. Centrifugal pump works on a centrifugal force. Yes, it works on centrifugal pump works on the centrifugal force. In centrifugal pump, water usually enters parallel to the plane of the impeller. No, the water enters perpendicular to the impeller. Let's take the example. So the water will come parallel to the surface. So water will go inside, and because of the rotation, the centrifugal force will throw the water outside. Because of the rotation, the water will be thrown outside, and it will rotate, and it will go up. So the water uh, will, if I make it like this, if I make this thing like this, these are the veins. So water will enter. I'm making this thing here, and it will be thrown outward. That is centrifugal force. Because of the centrifugal force, it will be thrown outside and it will go up. So that so in centrifugal pump, water usually enters perpendicular, not parallel. So perpendicular it will enter, and it will go enter out. Then it will go through this delivery pipe. Like this, the centrifugal pump works. Factors that are important in deciding the size of pumps are: flow needed at the point of connection to the distribution system, fuel consumed, discharge head. So there are only two parameters which are required to decide the pumping requirement, or the horsepower of the pump. So one is the how much discharge we need to provide, and how much head, up to which height, from which level to which level is provided. From what level to which level we have to provide the water. Let's take the example. Suppose This is the river. Let's say this is the pond. And we need to discharge, we need to supply water to a tank. So if we use a pump here, so we need to provide supply at the top, not at the bottom. Remember this thing. So we need to know how much is the head, at what height we have to provide the water, and at what rate. This is the rate, and this is the height. These two things we need to know. Fuel consumed is not a primary thing which on which we focus. This is the second reason. Factors that are important in deciding the size of pumps are, these are A and C. A and C means answer is D. Correct. The lift against which the pump should work is taken as, the lift against which the pump should work is taken as dash of suction lift, discharge lift, and head loss. So let's see that an example. So so this is the suction side. Because this pump is taking the water inside. This is kind of pulling. This side pull, and thus that side is push. So where pull is there, it is called suction side, and this side is called delivery side, because the water is getting delivered after this. It's called delivery side. So the head here, this is I will use different color. So this head is called suction head. This head is called, so from till this level we need to supply whatever the head is here. This head is called delivery head. Delivery head, suction head. Okay. So in the previous question, so this is called suction lift, discharge lift. So this is called suction lift, discharge lift, and there are bends here you can see, and there are friction. The water is flowing in the pipe, so there is pipe friction, entry loss, exit loss. Sometimes expansion is there, so those expansion loss, bend is there, bend loss, while curve. So all these losses we have to count, and then we can say then that will be taken as the total head requirement for that pump. So that will be the sum of the suction lift, discharge lift, and head loss. Dash pumps can increase pressure and can be located anywhere in the pipeline. So what is the name of the pump? Can you recall? Gas pumps can increase pressure and can be located anywhere in the pipeline. These are booster pumps. Booster pumps can increase pressure and can be located anywhere in the pipeline. What are horizontal and vertical wells? What can you understand from the name horizontal and vertical wells? So don't get confused with the names like what is horizontal, what is vertical. So first thing what we will understand, if this is the pump, this pump, I'm just making it as a block diagram. So this pump can either transfer the water horizontally in the x direction and it can transfer the water in y direction. So this horizontal and this vertical thing is not at all connected with this horizontal. Sorry, this is not well. Pump. So this has nothing to do. This horizontal distance and this vertical distance has nothing to do with the name horizontal and vertical pumps. So the thing is that when better read, it will give you an idea. So horizontal pumps. So pump shaft is positioned horizontally parallel to the ground. So the shaft which will rotate is positioned horizontally parallel to the ground. That is called horizontal pump. And the pump shaft is oriented vertically perpendicular to the ground. So if the shaft is like this is the shaft, it will rotate like this. It will rotate like this. And it has here the impeller perpendicular to the ground. So this is called vertical pump. This is horizontal pump. The shaft, when the shaft is positioned horizontally, so this is horizontal. This is the shaft which will rotate. So if it is parallel to the ground, then it is called horizontal, and when it is vertical, this this is called vertical pump. That's it. So vertical pumps are mounted above the pump, and the pump is typically installed below the motor in a vertical position. You can see in the slide also you can understand. They are suitable for installation where floor space is limited. Head or total lift is equals to, we understood this, total head or total lift, this suction plus delivery plus loss. We understood about this thing, and loss we will understand. In this we'll consider only major losses mostly for now, but in specifically we have to consider all the losses: bend loss, expansion, contraction, entry loss, exit loss. So that all loss we need to consider in this part. So suction lift is difference between low water level and pump is called suction lift. That here. It is just diagram. Low water level and this pump is called suction head. And similarly, difference between the point of discharge and the pump is called discharge lift. So This head loss HL can be calculated using Darcy-Weisbach formula. So this is an empirical equation for determining the head loss due to friction along a given length of pipe to the average velocity of the fluid. So the fluid here is, so the fluid considered is incompressible. So here it is liquid means water. So the head loss in pipe can be calculated using this equation F F dash LV square by 2 GT. So here the velocity V is the velocity, L is the length of pipe, D is the dia of the pipe, G is acceleration due to gravity. So this F is F is Fanning's friction factor and F dash is Darcy's friction factor. These all things you might have studied in fluid mechanics. Define suction lift. So the suction lift is the difference between the point of discharge and pump. No. Work done by the pump in raising the water. Yeah. Difference between low water level and pump. Yeah. This is the friction loss in the pipe. No. So work done by the pump in raising the water. This is not the suction lift. So this is the suction lift. The answer is C. Difference between the low water level and the pump. The work done by a pump in raising water up to a height h is called horsepower. Which of the following statement is correct regarding the pumping mains and service reservoir? Pumping mains and service reservoirs. For fixed discharge, as a diameter of pumping mains increase, the velocity of flow also increases and leads to higher frictional head loss. So what is A saying? A saying that discharge is constant, fixed discharge means Q is constant. Q is constant. The diameter of pumping mains increases and the velocity also increases. So discharge, if we use the continuity equation, area into velocity, so it is fixed. So the diameter of the pumping main increase. So if we increase the diameter, means area will increase. The velocity of flow also increases. So velocity should decrease actually, and leads to higher frictional head loss. So in A, first part is wrong. Let's check about the other part. F dash L B square divided by 2 GD. So what they are saying, so if we solve it, it will come out as d to the power 5. If you open this v square, v is equals to discharge by area will be pi by 4 d square and then whole square, then d to the power 4 plus into d, that will come out as d to the power 5. So if you increase the dia, head loss will it decrease. So head loss will decrease and they are saying higher frictional head loss. So both the parts of A are incorrect. Means if we are increasing the area, velocity should decrease, and if velocity decreases, we can directly say velocity decreases, head loss decreases. And with the dia also we can compare, if dia increases, head loss decreases. That's why A is wrong. As the diameter of pumping mains increases, cost increases. Correct. As the dia increases, the pumping mains, as the diameter of pumping mains increases. Yeah, correct. Because the length will remain same. It will not reduce the length. Service reservoirs increase the pressure fluctuations in the distribution system. No, we will study it later. Service reservoirs are made to reduce the fluctuations in the distribution system. This is wrong. As the discharge increases in the pumping means, as the discharge increases in the pumping means, the head lift increases. No, the head is something and discharge is something. So you are saying like, if you can see the question one, if I use pump one, so if I use pump one and pump two in parallel, I'm using them in parallel, the discharge will be Q1 plus Q2. But the head will not be H1 plus H2. Head will be H1 is equals to H2, provided if they have same head. So as the discharge increases in the pumping means the head lift? No, it won't increase. So the answer is C. Which of the following statement is correct regarding pumping mains and service reservoir? Answer is B here. As the diameter of the pumping mains increases, the cost increases. Darcy-Weisbach formula for determining head loss due to the friction along a given length of pipe to the average velocity of the fluid. Formula we studied is FLV square by 2GD. FLV square by 2G. So the answer seems to be the D. Yeah, answer is D on. Consider the given figure of the mass curve for estimating the storage capacity of the water. What is the answer for this? You might have studied. Can you tell? You can text. So the answer would be A plus B. That we will understand after some time. What is the typical suction lift limit for pumps placed above water level? This is 5 meter. Which type of valve is not used in the suction side of the pump? These are check valves. What is the purpose of surge tank in the pumping station layout? The purpose of surge tank in the pumping station layout is to regulate the flow. A service reservoir, distribution reservoir is used for. So it is used to balance the fluctuating demand in the distribution system. So what is this fluctuating demand and how will it balance? That we will study. Okay, that we can study now. So the fluctuating demand is, we know we have maximum hourly flow, we have maximum daily flow, we have average flow. So let's take a day, let's take June 15 is the hottest day, and on that hottest day there there is 1 hour, let's say 9 to 10 a.m. we have maximum hourly water requirement. So maximum hourly water requirement is, let's take 350. Let's take 350 liter per hour per day. 35 liter per hour per person. Let's take it. I'm just taking a general example. Liter per capita per day. Suppose we have in a community we have 100 people, and 100 people will require at that in this hour they will require 100 into 35 liters per day. So for this community of 100 people it will require 3500 liter per day. This is a real case scenario. Let's take an example. There is a community of 100 people. Okay. So for a community we have maximum hourly, maximum daily flow, average flow. So on the day of June 15th, that is the hottest day. So at 9 to 10 p.m. the maximum water requirement per hour was observed as 35 liter per capita per day. And so for a community of 100 people, this much water is required. But they are taking the water from a river source. They are taking the water, let's take, which has a limited water supplying capacity. Let's take 100 liter per hour. 100, not 1000. I'm sorry, 1000 liter per hour. Only this much water can be supplied. So what can we do? So this demand, this extra 2500 from where we will bring? So extra 2500 liter per hour required. So extra 2500 liter per hour required. That means here we have a reservoir. That means it should have 2500 liter per hour of maximum water storage capacity. Then only we can serve the demand of the society. Understood this much? And this was the case one. Let's take the case two. So here, what was the criteria? The water treatment plant must understand. So here, what is the flow chart here? So this is water treatment plant. From water treatment plant, it has limited water treatment. It was treating at 1000 liter per day, uh, per hour. Then it was given discharged to the and water was discharged to the distribution service reservoir. So from intake capacity was how much? 1000 liters per hour. But here in the community, we may need water at maximum hourly flow. So that's why instead of directly supplying, through water treatment plant to this community, we provided a service reservoir here which can reduce the fluctuations. So we'll not go through this path, we'll go through this path, then we'll supply. So it will have some extra water which can be used during uh, when there is requirement of extra water. This is the use of this service reservoir. And in case 2, during winter, let's take the example of December 15th. We only need 5 liter per hour per person, and we have 100 people. 100 into 5. The requirement is 500 liter per day. So in that case, we are treating extra wastewater. We are treating extra water. So in that case, we should have a capacity to store the excess water. Excess water storage. The capacity of the service reservoir can be calculated with the help of mass curve method. So in this mass curve method, what we will do, we know cumulative, we know supply, we know demand, we know supply, we know demand, and then we need to calculate, we need, like this is the time, 0 to 1, 1 to 2, 2 to 3, this is R, 3 to 4, likewise it will come till 12 noon, till 12 night. So we know supply, we know demand. We need to add and then we will find cumulative supply, and then we will find cumulative demand, and then we will plot these three: time versus cumulative supply, cumulative demand. So here I'm plotting this. This is cumulative flow. So let's say our supply, the demand is fluctuating. The demand is fluctuating. Here, what was the case? 500 liter per day, but we were treating 100 liter per hour. So it was R not R. Sorry. We need to store the extra water. So here, this is the cumulative demand. Cumulative demand. Cumulative demand. and this will be the cumulative supply. This is the cumulative supply. And this is 0 to 24 hours. So it is plotted between time and cumulative flow. So what is happening here? We'll understand it. So we have two things here. We have two things to note. One is ordinate and second is slope. Ordinate will tell means difference in ordinate. Difference and difference in slope. Difference in ordinate will tell whether it is surplus or whether it is wait, here we can say. So this is, let's take at t is equals to 4 hour. At t is equals to 4 hour, the cumulative demand is more and cumulative supply is less. This is case 1 or case 2? The demand is more but supply is less. So this is case 1 which we discussed now. And here the cumulative supply is more, the demand is less. This is case 2 during winters, or in a day also we can say this case 2 is for night time. During night, during day, what will happen? During daytime the supply will be less than the demand. So at this time we should have some excess storage. Okay, I will try to make this is the reservoir I'm making. So at t is equals to 0, we don't have water in the service reservoir now. Let's assume that. At t is equals to 0, this is at t is equals to 0. We should have, at t is equals to 0, we should have some water. And as the time is increasing, the demand is more than the supply. The demand is more than the supply. How? Theta. Demand is more, supply is less. You understand? This is A, this is B. I don't write, let's write it as XY. X is the Y ordinate and Y. So here X is greater than Y, means demand, cumulative demand is more than cumulative supply. So at this level, and if you see the slope also, the slope at this instant of demand is more. If the slope is more, when the rate of demand is more, so then this will go down. So it will go down, and if you see in this phase, this is phase 1, this is phase 2. The phase 2 is still here. In phase 2, the slope is less than this slope, theta 1, theta 2. In phase 1, theta 1 is greater than theta 2. In phase 2, the theta 1 is greater than theta 1 is less than theta 2. Theta 1 is less than theta 2. So here this supply is still less than this, but the slope of supply is more, so it will fill. Slope of supply is more, so it will fill, because theta 1 is smaller than theta 2. Theta means theta 2 is supply curve, so the supply is more, so it will again fill here. Then what is happening in the third zone? We can see again this theta theta 2 is no, this is theta 2, theta 1. Okay, theta 2 is greater than theta 1. It will again go up for phase 1, for phase 2, for phase 3. So in phase 3, what will happen? It will again, so theta 1 is less than theta 2. If theta 1 is less than theta 2, it will again go up. Theta 1 is less than theta 2, means theta 1 will signify the rate of supply. Theta 2 will signify the rate of demand. The demand is less, but the supply is more, so it will fill till this extent. And in the phase 4, you may see this is theta 1, this is theta 2. Will again come down. The water, so this signifies the water level. This will happen in the phase 4. But same thing, theta 1 is greater than theta 2. So these are the concepts of service reservoir. So likewise, you will plot this curve and you will gain insight from this curve. So what will happen here? So this will tell, I will make it. So this will give us the maximum A and B. So this will give us how much maximum water should be kept in the reservoir, and this much space should be available so that excess water may not come out of the reservoir. So this should be the A plus B should be the total capacity of the reservoir in terms of fluctuation. But in addition to this, we have some extra storage for the fire demand and In case of emergency also, we have two more things to add in the service reservoir formula or the volume requirement. So service reservoir design depends on reservoir capacity, topography of site, subsoil, what is the soil type. So there are different varieties of soil. So based on that we will design. And what is the cost of material, whether concrete, reinforcement and formwork. Total storage capacity of service reservoir equals to, it is equal to balancing storage uh, balancing storage plus breakdown plus fire storage. For the balancing storage we discussed now, so that is used for equalizing or balancing the variable demand against the constant supply, which is known as balancing storage. Breakdown storage, so water is stored as a reserve during breakdown time, 25% of the total capacity or 1.5 to 2 hours of average daily supply. So when treatment plant cannot work, example when there is a flood, cyclone or earthquake, so we don't have electricity at that time, so we can't supply water. That's why we need some extra water to supply to the community. And we need water for the fire storage. So here we can see it. It will take some time. Do you have any doubt till now? You can ask. Any doubts till now? Can you hear me? Reservoir reservoir capacity is determined using mass curve method. That whatever the curve we draw now, that is mass curve method. It is mass curve. So this is the end of the session. If you have any doubt, you can ask. So I think we can close the session now.